Okay, everyone. In this session, we will talk about chapter 3, torsion. In chapter 2, you learn about stress generated by uniaxial loading. Uniaxial loading divided by two kind of loads. One is tension, another one is compression. The one that you will do in the lab, or that you have done in the lab, is the tensile test. Yeah, session Monday have done tensile test. By the way, you can also do compression test. Okay, from tension or from tensile test, from compression test, you can get mechanical properties. By the way, there is also torsion test. From torsion test, you can get mechanical properties as well. So the mechanical properties you get from tensile test or compression test is considered as the basic mechanical properties because it is under normal stress. Michelle, what is the symbol of normal stress? It's a sigma. Sigma is a sign for normal stress. We also learn about another type of stress, which is shear stress. Shear stress is depicted by tau. What's the similarities between normal stress and shear stress? The formula is force over A. It's always force over A because stress is Pascal. Pascal is Newton over meter squared. So you should be aware that no matter what mode of loading your specimen accept or subjected, your stress will always be Pascal. Normal over Newton over millimeter square or meter square. Okay. If tension or compression load generate normal stress, what kind of stress torsion will generate? Moment? Okay, that is why we have to learn about torsion. Look at me. I am doing these activities, this movement. In bahasa Indonesia we call it pelintir, puntir, jewer, putar. This is how the load is applied. The load is applied to this spindle marker by applying a torsion. This is how you apply torsion. Therefore, in a car, you don't call it moment or you don't call it tension compression because the power from your engine is transferred to the wheel by shaft. The shaft receives torsion load, torsional load. We call it torsional load. This is how it is. Then I'm back to my original question. If tension or compression generate normal stress, torsion will generate torque. What is the difference between torsion and torque? At what condition you will use torsion instead of torque, but another condition you use torque instead of torsion? By the way, they are the same. Torsion torsion is its movement. Torque is the load. You are applying torque. The torque is applied. This movement is torsional. Therefore, it is torsional. The adjective is torsional. Okay? Yeah. Now, let me explain what kind of stress torsion can generate. A quick guess, Sean Lim. Pick between normal stress or shear stress. Shear stress, I think a good pick. Let's prove. Okay, this is how a shaft looks like. It is connected by a turbine or an engine. The engine generates torque. The torque is transmitted to the shaft to rotate generator. Generator create energy, or vice versa. You apply a voltage, then your electric motor will rotate, creating a torque. The torque is transmitted via shaft. The shaft will then rotate your turbine. Okay? So torque is everywhere. Torque is everywhere. The reason why we need to define what kind of stress is the same as what we discussed when we talk about force. We want to know how intense, how high the pressure, how stressful it is when a torsion is applied to the body. Remember when we talk about F, this is F related to uniaxial load. This generate delta. Delta is displacement. You want to correlate this. You cannot. What you do is you first convert, force becomes what? Becomes stress. F becomes stress. So sigma. The delta you convert it becomes strain. What is strain? Epsilon. Good. And these two are connected by Hooke's law, by Young's modulus. Correct. Sigma is E epsilon. This is also similar when we are applying a torque. Torsion. You would like to know how much angle, twisting angle we call it. Kalau di Jerman tuh berapa? How much twisting angle is generated? How much movement, elongation that is generated? You don't know. So you would like to know this. Phi. Twisting angle. But you don't know how to relate this. Therefore, you change torsion becomes stress as well. And as a clue, it becomes torsion. Shear stress, tau. Between tau, this phi need also to be translated into strain. The strain for torsional movement is gamma, because shearing is gamma. The angle, remember? Okay. So, what relates tau and gamma? Young's modulus. Can you use E? You don't think so? You are correct. So, we call this as G. Remember? G is the shear elastic modulus. We call it no more Young's modulus. It is elastic modulus. Elastic modulus under normal, elastic modulus under shear. So there is a relationship between E and G, by the way. Okay? Now we will try to figure out how torque can generate tau. Okay? You are applying a torque. Torque is, what's the unit of torque? Newton meter. Torque is generated by F times distance, F times radius. Okay, so if you have a torque around here and this is your shaft, you put a sectioning method to the shaft, you will see on the surface of your shaft, there is a shearing force, F. This F is located somewhere on the surface with a distance rho. Rho is the radius of this small element. If you add, listen to me, if you add the whole element at which every element has F times distance, F times distance, F times distance. You add those F times distance together, it becomes the total torque you're applying. So similar like the way you are applying the uniaxial load. You apply uniaxial load, F, compression, tension, internal force will be generated, perpendicular, opposite. Michael, follow me, right? This one, yes, you are applying a torque counterclockwise. It has to be cancelled out by the internal force. The internal force should create a torque in a clockwise. So this is in equilibrium. You are applying a torque counterclockwise. The internal force generated should be clockwise. So this F representing torque generated at this location. If you integrate the whole surface area, you will get torque. Okay, this is the integration. Torque is equal to the integration of dF times rho. Rho is the distance from the axis of your shaft. Okay. This is the small element that we talk over here. If you take out this, this is the 3D, the 3D shape. As you are applying an F, then this is the area that you are applying. Okay. Tau is described by F over A, in which A is this one. Okay. Therefore, that F can be replaced by tau, that is generated on this surface. This is the tau because of the F. F is there, you then divide it by the area at which or on which the F is applied, it becomes tau. So that F, which is actually originated from the torque, becomes tau. So that's the process of how a torque can generate tau. So let me repeat. If tension or compression test or tension or compression load generate normal stress, torsion or torque will always generate shear stress. The direction of that F is following the direction of the torque. Okay, now the question is, how can we quantify tau? It is still in F. We need to change that F becomes T. Therefore, the function is not tau equal to F over A, but tau is equal to T blah blah blah. We don't like F. F is for uniaxial. We can be deceived. We can be tricked to always see F related to tau. Tau is related to the torque. So we need to express the formula of torque in a function of, the formula of tau in a function of torque. Now let's see this. You have this rod. The rod is fixed on wall B, and then you are applying a torque T at A. Because of you applying torque T at A, that position A will move from A to A prime.
Okay.
Follow me?
Yes.
Easy, right? You are applying at A, that position, particular dot A, will move from A to A prime.
Okay.
This is the movement. That is the displacement. If it is under uniaxial, that is the delta. But this time, because it is torsion, we call it as phi, or apa Delon?
Angle of twist.
Angle of twist, or twisting angle. So, under tension or compression, we call it as displacement. Under torsion, we call it as twisting angle. Remember when I told you, if I am applying a force F, the body will deform this way.
Yeah.
Remember?
Yes.
Remember? Okay. This is now becomes A. This is now becomes A prime. This is the twisting angle. This defines how large the torque is. The bigger the torque, the larger the phi, the twisting angle. That is easy. Therefore, we can translate this as a straight. Okay, let's go. Phi is proportional to torque. Agree? The larger the torque, the larger is the larger the displacement. Okay. However, you will also see that the longer your shaft, the larger phi will be. If this A is located close enough to B, the travel distance is no longer this arc, but this arc. So there are two parameters that control phi. Not only torque, but also its position from the fixture. If you work with L, half L, the phi will be half too. So it is linear. If you work with 2L, of course, the phi will get big and bigger. It is linearly connected. So therefore, it is inelastic, still inelastic. When you twist it too much until it exceed the yield point, therefore it cannot back to its original position, this relationship is cancelled because you are talking on the plastic zone, not in the elastic zone. So similar, in torsion, our formula is applied under elastic zone. Therefore, Hooke's law is applicable. Follow me? Okay. Del one. Tell me what's the arc if you have 5. How can you find the length of arc if you know the 5?
Using sine phi.
Sine. Correct. But because the angle is too small, sine phi becomes phi. So this trefoil distance, meaning the arc from A to A prime, can be expressed by phi times the radius. Radius times phi. Okay? That's what Delon just mentioned. So this is it. This is also similar. If you use the L as the radius times the angle over here, we call that angle as gamma. Follow me? If you're talking from the axis, that's the angle of twist. If you're talking from the clamp, from the fixture, you call it gamma. Gamma is shear strain. Shear strain, gamma, is proportional to the twisting angle. Similar to what I mentioned. Epsilon is proportional to Rafi? Delta, deformation. Epsilon, Radit, what's the formula of epsilon? Delta over original length, correct. Now we are reaching that point in which we can now define shear strain. If phi is the twisting angle, we have another angle that can define the same displacement. We call that as gamma. L gamma is also talking the same arc. So this is the relationship. Therefore, shear strain because of torque is defined by phi times radius divided by the L. L is the length of shaft. Okay? If you working at this point, this is 8. What if your shaft is bigger? Yeah, just make it bigger so the position can be moved to the outer space. You're working in the inner space, making outer as you move to the surface. So A can be located somewhere inside the shaft, but as you go to the surface, of course, the arc will also linearly increasing. So what we can tell here is the Y max, the gamma max, meaning the maximum shearing strain, occurred when the radius becomes the maximum radius, the larger radius. Or in other words, if you are applying a torsion, a torque, when is the minimum shearing strain occurred? if you are applying a torque on your shaft, can you tell me at which location the shearing stress minimum? At the center, correct. Why? Because no radius. Indeed, in the center, no torsion. The only place that is not twisted is in the middle. If a tornado comes, you try to find the middle. Therefore, you won't be twisted. Apa nama film ini? Twister.
Twister.
Ada twist. Zaman saya namanya Twister. Sekarang udah ada lagi kan Twister. Film terbaru itu. Tornado. Twister. So, Jarvis, where's the location of zero strain? Center. Center, in other words, if it is a shaft, what do we call the center? The axis. The axis of a shaft, no stress. Paling relax. But the most stressful, Sean Nabil, located where?
The edges.
What?
The edges of the shaft.
The edges wrong. Where is the farthest
Surface.
surface? Correct. So the most stressful position of a shaft under torque is at the surface. So if you are applying the torque too big, where will be the first location will break? Surface. So if you see your shaft crack at the surface, you know that is of course because of the torque. If you see your shaft crack in the middle, do not even think it is because of the torque, because the torque is minimum in the middle. Masuk akal nggak, Michael? So this is how mechanical engineer do diagnose. What's wrong with my machine? It keeps failing, it keeps vibrating. And then you open it up, you do overhaul, you look at the shaft, you look at the components and found out your shaft has a crack on the surface. You're smiling. But people keep asking why you are smiling. Because that smile meaning that you know the reason why the crack happened. It's because of the torque. So you now can complain to the operator. You apply the torque too large. The manual book says it should be around this torque, this Pascal. You might have applied too much, or you might have run it over the capacity. Okay? This is how the torsion, the cow is distributed. As Michael just now realized, oh, the middle has no shear stress. Yes, and the largest will be Sean Lim, as Sean Nabil mentioned that it is in the surface. We got this equation now. Gamma C equal to rho gamma. Or the ratio. Yeah? The ratio. Maximum shear strain over the C, maximum radius, equal to the shearing strain over radius. So we have this relationship. Now we multiply this relationship with G. Stephen, what is G again? Shear modulus. You multiply the shearing strain with the G becomes, Brian, shear strain multiplied by G becomes tau. Strain times G. G is the shear modulus. It becomes tau. What is tau? Shear stress. So this is shear stress. The previous slide shows this relationship rho over C gamma max. You apply similar way times G. Okay, now this equation becomes tau equal to the ratio of radius multiplied by tau max. So this explains the relationship. This is linearly distributed, meaning that when the rho equal to C area, when the rho equal to C, the tau will be equal to tau max. Okay, so we are talking about this one. From 0 to C defined by rho. Rho is the radius. In another class, rho is density. I'm sorry, in this class, rho is radius. Do not blame on me. It's blame. The textbook use rho. Let's use the textbook way. Okay. So we have this condition.
What is C again, sir?
C is the maximum radius. The farthest, the outer radius. Okay. Torque is equal to force times distance. Okay? Force times distance. Torque, yeah. Torque is force times distance. In here, torque, yeah. Torque is F times R or rho. The F is generated inside the shaft multiplied by its distance from the axis will generate torque. We have this equation in the early slide. Now, what I'm going to do is I will replace this. Therefore, I will write as tau multiplied by A multiplied by rho is equal to torque. Okay, and you would like to find this tau now. Get back to this equation. Tau multiplied by, the torsion, torque equal to tau multiplied by A multiplied by rho. But this A is the small element that I mentioned. Okay? If you then replace the tau here, comes to this equation, you will have this equation. Rho over C tau max will replace this. So you will have T equal to tau max over C integration of rho square dA. This rho square dA is called as the polar moment of inertia. This one. J is the polar moment of inertia. So let me repeat. From torque, you know that it is F times A. The F is replaced by torque times A. From here, you apply the torque, the tau from here, you'll get this equation. Then this equation result in another shape of tau, of a torque, equal to tau max J over C. And then you rearrange the equation, becomes tau max equal to Tc over J. T is the torque, C is the outer radius, J is the polar moment of inertia. Can you remember this equation?
I think J is different for F has its own J formula.
Yes. For example, this one. J is defined for a circular shape is 1 over 2 phi c power 4. C is the radius. If it is a donut shape, the J is defined by outer radius power 4 minus outer inner radius power 4. So J represents cross section. Now I would like to make you remember the equation. Sigma is F over A. With the same logic, we also know that tau is equal to F over A. From that slide, we have figured out that tau can be expressed as T C over J. F is the load, torque is the load as well. So I can arrange this becomes T over J over C. What I'm doing here is I am putting the whole load parameter in the upper part and dimension parameter in the below. If it is a circular shape, I will get what is the polar moment of inertia of a circular shaft? 1 over 2 P
R square.
P C power 4. Polar moment of inertia, not PR square. Okay. Then I can replace if I found J over C, therefore J over C, it will give me half of P C power 3. Power 3. The power?
Why is it power 3?
Yeah, power for it.
J is equal to
1 over 2.
half P C power 4. That's the power moment of inertia. If I divide this by C, if I divide it by C,
Yes, correct.
this becomes J over C equal to
I times C to the power.
so this equation becomes T over PC power 3 over 2, or it becomes 2T over PC power 3. So that's the equation for torque of a shaft. What you need to remember is just this one: the load over dimension, cross-sectional parameter. If for this one it is F over A, the F becomes T, the A becomes J over C. Yeah. Now you have sigma is equal to F over A. You have torque or tau because of torque is defined by TC over J.
So what is the unit of, what are the units of PC?
Good question. What is torque?
Newton meter.
Torque is Newton meter over PC power 3. So C power 3 is meter cubic.
Newton meters.
Oh.
It's again Pascal. So stress is Pascal. case study. Suppose you have this shaft A, B, C, D. You have A, D shaft. It is connected with gears and pulley, for example. Each of that gears and pulley receive torque. The gears at A get 6 kilonewton meter. The pulley at B get 14 kilonewton meter. This one get 26, this one get 6. My question to Rafi,
Yes.
okay, is it in equilibrium or not?
Makanya
I mean, we can do FPD first and determine.
Yes. Can you check whether it is in equilibrium or not?
Yes. Yes.
Yes. Why it is so quick?
As in, yes, we can check.
You can check. Proof that it is in equilibrium or it is not in equilibrium.
We can check. I haven't checked it. I think it is.
Check.
Okay.
Check.
6 plus 14, 20.
How are you going to check it?
if the force
Sigma torsion equal to
zero.
0. You have sigma x, sigma f equal to 0. You have sigma m equal to 0. So you have sigma t equal to 0. So do now, write sigma t equal to 0. Check whether this shaft system is in equilibrium. If sigma t does not equal to 0, it is not in equilibrium. So Nabil, tell me which torque is positive and which torque is negative.
One going to the right.
Hmm?
One going to the right.
A, B, C, D, tell me.
ABD.
Huh?
ABD is positive, C is negative.
Why?
C is the only one going against the...
No. The distance, the convention. Remember what? Counterclockwise is
Positive.
positive. Michelle, counterclockwise is positive or not?
Positive.
Positive. So at which location
AB
the torque is
is
counterclockwise?
ABD.
Is C. The counter A, B, and D.
Yeah.
Counterclockwise. Yeah. A, B, and D. Yes. So put the force times distance.
It's a matter of
Put
perspective.
the force times distance.
No, we have determined, right?
Yeah, the right hand rule.
The right hand rule. You're not using your left hand rule.
C.
Johan, A, B, C, D. Which one is positive? A, B positive, B positive. So you can add up this 6 plus 14 plus 6 equal to 26. Therefore, C should be 26. Where do you think the engine is located?
Inside of the car.
Okay, let me change my question. Where do you think the engine is connected to the shaft? At A, B, C, D.
At the end of this. At the axis of the center.
At A, B, C, D, where do you think you will connect the engine?
B. No, B. B. Big bang. A. What year it was?
Engine. The source of power.
I
In the middle of A and B.
Let me change to pulley.
C.
C. C.
Oh.
This is actually real. C is a place where you locate the engine connected with pulley, for example. So the engine is rotating. It is connected with pulley C, applying a 26 kilonewton. That 26 kilonewton is used to rotate ABD.
Oh, itu. Kenapa nggak dikemas? Kenapa nggak dikemas?
Because di tengah nothing. You have to put something. Therefore, the engine is connected to the shaft. You have a gear. You need to have a gear or pulley, right? Di tengah nggak ada siapa-siapa. It's a even no bearing. Okay. Let me ask Brian. Brian, tell me what is the internal torque of AB?
AB.
Stephen, what is the internal torque of BC? Ansel, what is the internal torque of CD? You are BC, you are CD, you are AB, you are CD. Ah. Twenty. CD.
CD ya.
CD.
CD is
20. AB. Ayo, selamat banget.
ya tambah 14.
I think
This is the same sectioning method as we applied in uniaxial.
Oh.
True, correct, wrong.
Okay. ABC.
What is the correct answer? Answer 6. What is the internal torque of AB?
Dipotong. Yeah. Yeah.
6.
Yeah.
This is a shaft A, D. They have B, C. Okay. First at A, it is applied by a torque of 6. At B, it is applied by a torque of 14. At D, 6. At C, 26. Sectioning method applies this at this two. So you do this, you will have 6 balance 6. Counterclockwise, clockwise. So the internal force, internal torque is clockwise torque, which is 6. Then similar way, you have 6, you have 14.
20.
Therefore, it is 20 kilo. Even you cut it from right hand side, that is also true. So you cut it from here. It has 6. It should be against this one 6. If you move this way,
6 minus
20. Everything is 20, the same. Yeah. After knowing the internal torque of each of the shaft, your job is to define tau.
Yeah.
Knowing that Knowing that shaft BC is a hollow shaft with internal radius of 45 millimeter and outer radius of 60 millimeter, determine tau max. Determine tau max.
Lo jadi 45 ya radiusnya tahu max di
The
pakainya
shaft at BC is a hollow shaft.
times
60 millimeter,
45
45 millimeter. Area, calculate the J.
So 2T over.
Calculate. I said not say. Calculate. Calculate. Yeah. Calculate.
Donat
Torque is equal to TC over J. From area, I will get J. From Stephen, I already get T.
Sir, which one is C1 and which one is C2?
Which one is C1? Which one is C2?
C1 itu inner, C2 itu outer.
Oh, okay.
This is C1. This is C2.
Oh, okay.
What I would like to find is tau max is equal to TC over J. Calculate. Ya, udah dapat? Calculate yourself ya. Biar terbiasa pakai kalkulator. Michelle got G already? Done?
J.
What is J?
Half pi.
Half pi?
Yeah, times. I think it's 2/4.
Ya, ya.
I got 13 million. 14 million. I don't know where it came from.
Meter.
That is in millimeter.
Oh, sorry.
Change it to meter. Meter power 4. Delon?
Meter kan? Ini millimeter. Bisa di-
1.3 millimeter square to meter square. Wait, gimana? Millimeter cube.
Oh iya.
What? Oh, 1
Millimeter.
Okay, let me know the number in millimeter power 4.
13,9 something. Power 4. 13,9.
Yang bawah awal tadi.
1.3960.
Kali dari kurung 60.
Meter square.
Kurang.
Okay, in millimeter again. Back to millimeter. 13.9
92
Yes.
millimeter.
Sama-sama.
power 6
Yes.
meter millimeter. Gitu, benar? Oh, benar. Tadi benar.
Jadi itu kalau millimeter.
Millimeter benar ya? Oke. 13.9 power 10 power 6 millimeter cubic. Kubik, power 4. Okay, now I can write this one. The T was 20 ya? 20,000. 20 times 10 power 3. What is the C? Michael? What C I should put here? C, I know. Focus.
Maximum.
Maximum rate.
C, not J. I'm not talking J. I'm talking C. What is C?
Outer radius.
The outer radius, because I'm asking the max. The max is generated at the surface. So T is 60. 8 millimeter, yeah?
Yeah.
Divided by J. J is 13.92 power 6. Hasilnya berapa? 80? 86.2 Newton over millimeter square, or it is 86.2 megapascal. Because millimeter square is 10 power 6. 10 power 6 is megapascal. If the allowable shearing stress is 65, the applied stress is 86. My question, will your shaft fail or not? Because exceeds the limit. Because Sean just mentioned it will fail. Now my question is, what is the safety factor? Safety factor is defined by the limit of the strength
Divided by the
divided by the applied.
Yeah.
65 over 88.
So it is
86.
65 over 86.2, less than 1. Yeah, 0. Safety factor of bigger than 1 is safety. Safety factor less than 1 is dangerous. Not dangerous, is fail already. Trouble. Yes. So you always want to design your structure with safety factor more than
Under one fail.
under 1 will fail.
Long time. Google sa Iya fail.
Okay, thank you. That's enough for today.
Lagi.